Have you ever wondered, why do writers and poets often compare beauty with nature? Nature is beautiful. It is not just something that we say, because we have seen so many beautiful places. But nature is beautiful. It's something that has been proven by science too. In the early 19th century, scientists formulated a theory which could accurately explain every natural phenomenon. With the help of this, we could measure the height of a building, find the range of a bullet, and even discover the planet Neptune. All of this happened for the first time in history. This theory was not just beautiful in name, but it was truly the most beautiful theory back then. Today, however, this theory is not considered the most beautiful one. But before we talk about the most beautiful theory of today, let me tell you what was this all-encompassing theory that was considered the most beautiful theory 150 years ago. It was called classical physics. Do you know when did classical physics come into existence? In the 17th century. Who were its proponents? Isaac Newton, Gottfried Wilhelm Leibniz, and a few other European scientists. These theories include mechanics, thermodynamics, optics, acoustics, electricity, and electromagnetism. This is why it was called the most beautiful theory at that time. Now let me tell you some of its characteristics. Number 1. Everything is made up of particles. Each particle has a mass and a velocity. With the help of these two, we can calculate where the particle will be after some time. In simple words, if we know the past and present of a particle, we can easily predict its future. Number 2. Energy can be transferred continuously. For example, if you mix hot milk with cold coffee, the temperature of both will gradually become the same. Here, energy is being continuously transferred from hot milk to cold coffee. Number 3. There are some physical quantities that can never be zero. They are called constants of nature, such as speed of light, gravitational constant, Planck's constant, etc. This theory could explain almost everything that happened in nature, from the motion of celestial bodies to the falling of a leaf, from the collision of two balls to the breaking of a glass. This was the most beautiful theory for more than 200 years. But what was its problem? Now here's the thing. You see that cup of coffee with hot milk that we talked about earlier? Its temperature will never reach absolute zero. Even if we keep stirring, the temperature of coffee will get closer and closer to room temperature, but it will never actually become equal to it. Same for anything else. You see, no matter how much you compress a spring, it will always have some amount of energy left in it. Similarly, no matter how much you slow down a moving object, it will always have some kinetic energy left in it. So basically, the classical theory predicted that every object with a temperature above absolute zero emits some amount of energy. This energy emitted by objects is called black-body radiation, but there was a problem with it. According to the classical theory, if an object had a temperature greater than 5,000 Kelvin, it would emit infinite amount of ultraviolet radiation. Now clearly this was not happening in reality. Ultraviolet catastrophe, this was called. So basically the classical theory failed to explain black-body radiation, and this became the biggest challenge before scientists of that time. Then came a German physicist named Max Planck. He proposed a very simple idea, which completely changed the course of physics. He proposed that energy is not transferred continuously, but in discrete packets. We call them quanta. In simple words, energy is transferred in certain limited amounts. Energy is quantized. This is why Planck's theory had a graph. See here, this graph matches with the experimental results. Not only did it solve the problem of ultraviolet catastrophe, but it also made other predictions that matched with reality. Planck's quantum hypothesis laid the foundation of quantum physics. According to classical physics, electrons revolving around the nucleus should continuously lose energy and fall into the nucleus. But we don't see this happening. This anomaly was solved by quantum mechanics. Electrons do not revolve around the nucleus in any energy level. They can go to any energy level. They can only go to certain energy levels. This is why we see atoms as discrete lines in emission and absorption spectra. If we go deeper into quantum mechanics, we see that the behavior of subatomic particles is inherently random. Due to this randomness, we cannot accurately predict the future of a particle. We can only predict the possibility of it. Now, do you remember what we said about the classical theory? We said that it could explain everything that happens in nature. Since quantum mechanics rejects this deterministic view, it does not explain everything. Yes, it explains things at the atomic and subatomic levels, but not beyond that. So what should we do? Should we reject quantum mechanics and stick with classical physics? No. Why should we do that? Can't we combine both of these? Yes, that can be done. And that is called quantum field theory. You see, for explaining the behavior of macroscopic objects, classical physics works perfectly fine. But for explaining the behavior of microscopic objects, quantum mechanics is a must. Therefore, a theory was needed that could explain both classical and quantum phenomena. In simple words, a theory was needed that could explain both the behavior of planets and the behavior of electrons. Albert Einstein provided the first piece of the puzzle. His special relativity showed that mass and energy are interchangeable. It also showed that nothing can travel faster than light. This removed one of the inconsistencies between classical and quantum physics. Later, scientists developed quantum field theory by combining classical physics, special relativity, and quantum mechanics. And this theory is considered the most beautiful theory today. Why? Because with the help of this theory, we can explain even the smallest level of interaction in the universe, whether it is between electrons, photons, forces, or any other fundamental particle. Now, do you remember why poets and writers compare nature with beauty? Because nature is beautiful, not just in words, but in reality too. See, when scientists formulated the classical theory in the 17th century, they believed that this was the final theory. They thought that nothing beyond this was possible. But a century later, quantum mechanics was born, which turned the deterministic view of the world upside down. And today, after another century, quantum field theory is considered the most beautiful theory. Maybe a century from now, this theory will cease to be the most beautiful one, and something better will come along. This is how the pursuit of knowledge takes place. It is a long and arduous journey. There will be progress. There will be failures. But progress will be made. Now, you might think that this video is all about physics, but it's not really. Sure, we started this video with Newton and ended it with quantum field theory. But the point of this video was not to teach you these theories, but to show you how these theories evolved over time. And in the process, we learned something very important. Do you remember what it was? Well, let me remind you. You see, for more than 200 years, the classical theory was considered the most beautiful theory. Then came quantum mechanics, which turned the deterministic view of the world upside down. And today, quantum field theory is considered the most beautiful theory. Maybe a century from now, this theory will cease to be the most beautiful one, and something better will come along. Now, in this entire process, we devoted a lot of time to classical physics. We explained what it was, what were its characteristics, what was its scope, and finally what was its problem. But do you know what? At no point did we talk about who was behind this theory, who were its pioneers. We did not talk about their struggles, their failures, and their contributions. See, whenever we talk about theories, we talk about their practical results, but we rarely focus on the people behind them. But it should not be like this. Just like a theory is judged by its practical results, your skills should also be judged by your practical experience. A degree or certificate may open the doors of opportunities for you, but it is your skills and practical experience that will help you succeed. I hope you liked this story. If you did, share this video with your friends and family and let them know what you liked about it. I am Gaurav. You can find me on social media. If you like such videos, subscribe to my channel. Thank you for watching.